Hello everybody, I'd like to tell you a little bit about ordinals today, and I'll start with a brief introduction to what ordinals actually are, the mathematical concept of ordinals. Turns out an ordinal is an equivalence class of well-ordered sets. A well-ordered set is a set that's totally ordered and such that every non-empty subset has a smallest element. Most of you already know many examples of well-ordered sets. For example, every finite set, if we have an integer, a positive integer n, then that represents a finite set with n elements. You could pick as representatives the elements between 0 and n minus 1 with the usual order. And that is an example of a finite ordinal. The smallest infinite ordinal, you can see down here, is usually denoted by omega, the Greek letter omega, and it just stands for the set of all non-negative integers, the natural numbers, again with their natural ordering. Now, using that, you can form some other well-ordered sets. For example, you can take products of omega by itself. So for any non-negative integer n, omega to the n would be the set of all n tuples of non-negative integers, where you first order by the rightmost component, then if the rightmost components are equal, then you order by the second rightmost, and so on. So for example, if you have omega squared here, then the smallest element in there is the pair which has both entries 0, and then we start counting up in the first component 1, 0, 2, 0, and so on, and that goes up indefinitely. And then at some point, the next, we get, if we start counting up in the second component as well, we get the pair 0, 1, which is greater than any other pair that has a 0 in the second component. Since we order, the most important component is ordering is the second component, not the first one. So we get 0, 1, 1, 1, 2, 1, and so on. And then we get all the entries which have second component 2, and so on. And then finally, another example is denoted by omega to the omega. This is just the union of all of these finite Cartesian products, powers actually, omega to the n. And you can think of it as the set of all tuples of finite length. They don't have to be the same length, they can be of different length, but the length is still finite. Again, with entries being non-negative integers, and we choose the lexicographic ordering with the rightmost component being the most important one. Okay. After this very brief introduction, let's look at what we can do with ordinals. So, like regular integers, ordinals can be added. What does that mean? If we have two ordinals, we take the union of both of these, but that has to be the disjoint union. So even if they happen to have the same elements, we artificially make them distinct, for example, by introducing indices or something like that. And the addition is not commutative, so whatever is added on the right, by default, all of the elements of the component on the right are strictly greater than all of the components, all of the elements of the component on the left. Beyond addition, we can talk about multiplication of ordinals. So the product of two ordinals is just we take the Cartesian product, again with the lexicographic ordering from the right. And exponentiation, we've already seen an example. The standard definition of exponentiation of sets is you would consider all functions from the set that's in the exponent to the set that's the base. But this difference here with ordinals is you only consider functions with finite support, meaning with finitely many elements that are non-zero. And again, we consider lexicographic ordering from the right. So here are some examples. We can do this in Maple. We load the ordinals package. And we see that the package offers all of these operations here. And the first two that you can see are addition and multiplication. Multiplication is denoted by a dot and not by an asterisk because it's also non-commutative multiplication. And then a little bit further back, you can also see the little hat denoting the powering operator. So Maple understands the omega, so it can just enter the Greek letter omega and will be interpreted as the ordinal omega. If I just add the ordinal omega, and on the right I add the ordinal 2, so that's just the two-element set, nothing happens. So this will just remain inert as it is, but it denotes a new ordinal that we haven't seen before. Namely, we first have all the integers marked in blue here in this example, and then on top of that, as larger elements that are larger than all the integers, we add two more integers, namely 0 and 1, and those are highlighted in green here to make clear that we have the disjoint union. So the green 0 is different from the blue 0, and the green 1 is also different from the blue 1. So those are different elements. We can also use the inert addition operator here, so the ampersand plus, and that will just display the addition without actually executing it, while on the right-hand side of the equality sign, where we have the 2 plus omega, we will see the result of the addition. So what you see here is on the left-hand side, you see the 2 plus omega. That's the inert operation, and it's indicated by the fact that it's grayed out. And on the right-hand side, you see the result of that operation. So if we actually perform the ordinal addition of adding 2 on the left to omega, we get omega back. Now, why is that? Why don't we just get 2 plus omega, for example, or omega plus 2? Why is it not commutative? And the reason is, if we look at this picture here at the bottom, what we do here is, again, we form the disjoint union. But this time, the finite set is smaller. The green numbers in this disjoint union here are smaller than all the blue numbers, right? So first we get the green 0, then the green 1, then the blue 0, then the blue 1, then the blue 2, and then all the other blue numbers. But this is isomorphic to just the integers themselves. So if we just, an isomorphism would be that we associate the green 0 with the 0 in the integers, the green 1 with the 1 in the integers, the blue 0 with the 2 in the integers, the blue 1 with the 3, the blue 2 with the 4, and so on. And then that structure that we get is exactly the same as the structure we have here. So this basically covers everything. If we add other integers than 2 to omega, exactly the same thing happens, just the lengths of the finite pieces are going to be different. So the first thing that is different from what we had so far happens when we add omega to itself. So let's see what happens. So again, we're using the inert addition operator. So on the left, we see what omega plus omega is displayed as, and on the right, we see what the result is. And the result is the product of omega and 2. So what is the product of omega and 2? On the left-hand side, we have the sum of omega by itself. So this time we have 2 complete copies of the integers, of the non-negative integers, the blue ones and the green ones. And on the right-hand side, multiplication, if you look at the top of the screen, you see that multiplication is defined as the Cartesian product. But this time we have the Cartesian product of omega with a finite set 0, 1. So there's only 2 copies of omega, those that have the 0 in the rightmost component, starting with 0, 0, 1, 0, 2, 0, and so on, and those that have the 1 in the rightmost component. And that's it. There's none with a 2 in the rightmost component or a 3, and so on. And you can easily see that those are isomorphic as well. If we would just color all the ones that have a 0 in the second component in blue and all the ones that have a 1 in the second component in green, then we get exactly the same thing as on the left-hand side. Okay, so what happens if we keep adding omega to itself? We get omega times 3. That's not too surprising. What happens if we actually try to multiply? So we've already seen what would happen if we multiply omega times 2 from the right. We just would get omega times 2 back. But what happens if we multiply 2 from the left? So again, we use the inert multiplication operator ampersand dot. And on the right-hand side of the equation, we use the non-commutative ordinal multiplication operator dot, which performs the actual multiplication. And the result is maybe somewhat surprising. 2 times omega is omega. Now, why is this the case? 2 times omega, again, is the Cartesian product, where again, where this time we only have 0 or 1 on the left. So the smallest element is still 0, 0. The next smallest one is 1, 0. But then, since the set on the left-hand side is finite, we cannot keep increasing the left component. We have to instead reset the left component to 0 and increase the right component. So we get 0, 1, and then 1, 1. And then again, we have to start at 0 in the left component, 0, 2, 1, 2, and so on. And again, it's easily seen that this is isomorphic to the integers themselves. We could just rename 0, 0, this one here to 0, and this one to 1, and this one to 2, and this one to 3, and so on. And then we could get exactly the same ordering, not necessarily the same properties regarding arithmetic, but the same ordering. So isomorphism here in this sense is to be understood as isomorphism with respect to the ordering only. Okay, so what happens if we multiply by 3 from the left instead of by 2? You can almost guess that nothing changes. The result is still omega. So the next interesting thing is what happens if we multiply omega by itself. So that we've already seen. That should give you omega squared. So that's the set of all ordered pairs of integers with lexicographic ordering from the right. And if we do it 3 times, we get omega cubed, and so on. Now here's a first non-trivial example where we're mixing addition and multiplication. So we're multiplying from the left omega by omega plus 2. And what we can see here is that in this case there's some sort of distributive law that holds. Namely, we can just multiply this out. So we multiply omega by omega, get omega squared. And we multiply omega by 2 to get omega times 2. However, if we do it the other way around, there's no such distributive law. So one key thing with ordinals is that things that happen on the right are usually nice and they're exactly the way you would expect, and things that happen on the left are somewhat unexpected. So what happens here, if you multiply by omega plus 2 on the left, all the lower order terms, so the plus 2 basically here in this case, get ignored, and only the highest order term matters. Okay, so going beyond multiplication, we can use exponentiation, and here on the left-hand side, we use the inert powering operator ampersand hat, and on the right-hand side, we use the regular powering, which is entered in 2D math as an exponent. And this says, so the inert powering operator is indicated by having these grayed out brackets around the base. So 2 to the omega, its claims, is equal to omega itself. So again, this may be a little bit surprising. And here's an illustration why that happens. So we have to recall what the definition of exponentiation is. That's all the functions from omega, so from the integers, into the finite set of 2 elements. So 0, the function values can basically be 0 or 1, but only finitely many of them can be non-zero, so we can have only finitely many ones. So basically we have infinite sequences of 0 and 1, but with at most finitely many ones. And equivalently, we can consider this as finite sequences of 0 and 1. We just don't display all the trailing infinitely many zeros on the right. So basically, 2 to the omega is the union of 2 to the 0, which is just a single element set, the empty tuple, with all the 1 element tuples, 2 element tuples, 3 element tuples, 4 element tuples, and so on, with entries being just bits, 0 and 1. Okay, so basically 2 to the omega is a way of writing down all the integers in binary notation, with the only distinction that we're writing them in the wrong order. So normally we would write the most significant bit first on the left, but this time we write the least significant bit on the left, and the most significant bit is on the right. and you can see that down here. That's an illustration of what 2 to the omega is like, and that shows also that 2 to the omega is equal to isomorphic with respect to the order. It's isomorphic to omega itself. So if we try the same thing with 3, it's not too surprising. That would be the ternary representation of all the integers. It's still isomorphic to omega. Now let's try an exponent that's a little bit more complicated. So we take omega plus 2 as an exponent instead of omega itself. And the result is, again, on the right side, this is distributive in the way one would expect it. I mean, you get 3 to the omega times 3 to the 2. And 3 to the 2 is just an exponentiation of integers, which behaves exactly like one would expect in the integers. And then we get a multiplication of 9 on the right. If we do the same thing with omega, not much happens. Here's another example where we're multiplying omega to the omega and omega squared, and we get the same result as before. So also here, this example illustrates that on the right we have the distributive law, which holds, the one that we would expect. But again, on the left, this is not the case. So if we take omega plus 2 to the omega, then again, the only thing that matters on the left basically is the highest power, the highest order term that appears, namely omega itself, and the 2 gets absorbed. Okay, so these were some simple examples of ordinals and their arithmetic. Now, how would one represent ordinals? And we've already seen examples of this when, for example, in line 15, equation number 15, nothing actually would happen because the right-hand side is already in a normal form. While here, if we do a different type of operation, we arrive at the same result, but again, the result basically has been brought into some kind of normal form. So what is this normal form? This normal form is written down here. So we have a power of omega times a coefficient on the right, plus another power of omega times a coefficient, and so on. So this is called Cantor normal form, after the German mathematician Georg Cantor. And so the coefficients C1 up to Ck are positive integers, and the exponents, they can be ordinals recursively. So there's a difference here to what you would call a polynomial. This almost looks like a polynomial in omega, except that the exponents not necessarily need to be integers. They can be ordinals themselves. And another condition is that the exponents have to be ordered according to the ordering of ordinals. There's also another technical condition, namely the Cantor normal form is called proper if the first exponent is actually less in the ordering than omega to the first exponent. This may look like a funny condition, but there is actually ordinals that satisfy these conditions, but they will not. We will not talk about those in this talk here. So here's an example of how I can directly construct such a Cantor normal form. In Maple, I would use the Ordinal Constructor, and I pass in a list of pairs where the first component in each pair is the exponent, the e, and the second component is the coefficient. So the e1 would be omega in this case, so remember that the exponents can be ordinals again. The c1 would be 3, e2 would be 3, c2 would be 5, and so on. And it's being displayed exactly in this form above, except omega to the 0 is not explicitly written, it's just omitted, so we can have something like a constant term. So the 0, the comma 4 here in this example corresponds to just the constant term 4 at the end. Okay, what does the Cantor normal form tell us? Since the coefficients are integers, they could in theory be replaced by just additions. So this is not a normal form yet. So I could have omega to the e times 2 plus omega to the e times 3, for example. Actually, that would not strictly be a Cantor normal form because the exponents are equal. They are not, the first exponent is not greater than the second one. But I could relax my representation here and allow the exponents to be equal, some of them, and then I wouldn't need any of the coefficients at all. So I could, for example, if I have omega to the e times 2, I could just replace that by omega to the e plus omega to the e. That would give me another kind or another version of the Cantor normal form, which shows that multiplication is not really required. I already mentioned that there are ordinals that for which this equation does not hold. So you can see one here. There are ordinals for which I said previously for which the equation doesn't hold. What I meant is for which this inequality doesn't hold, but instead equality holds. And the smallest such ordinal is called epsilon to the 0. And one representation for that is to say that is the set of all proper ordinals. Another way of thinking about this is to say, well, this is if we keep powering omega infinitely often and take the limit of this construction, basically, that would also be epsilon 0. But epsilon 0 is beyond of what I want to talk about today, I want to focus from now on what Maple can do, and Maple can represent all ordinals that are less than epsilon 0, basically. Okay, however, there are only countably many of those, but the picture is quite complicated. So let's only start with the first row here. So these are the smallest ordinals at all. So 0 is the absolutely smallest ordinals. There's no smaller ordinal than 0, representing the empty set, basically, set with one element, set with two elements, and so on. After we go beyond the integers, the first infinite ordinal is omega itself, the set of all integers. Omega plus 1 is the set of all integers plus one greatest element to the right. Omega plus 2, we've already seen, that's the set of all integers plus another element to the right. So there's two elements that are bigger than all the integers, and one of them is the greatest one, and so on. Then again, we have infinitely many of those. The next one is omega to the omega, which is omega plus times 2. Again, we can add 1, 2, and so on. We get to omega times 3, we can add 1, and so on. We get to omega times 4, and so on. We get to omega times omega, which is omega squared. We can add 1, we can add omega, and so on, and so on, and so on, and so on. We get to omega squared times 2. Can do all these things again. We get to omega squared times 3. Can do all these things again, and so on. We get to omega cubed, with which we can again add the same things on the right. We get to omega to the 4. We get to omega to the 5th, omega to the 6th, and so on, omega to the omega. That's already fairly complicated, omega to the omega, just thinking about it, but we're by far not done yet. So again, we can add things to the right, we can multiply it by earlier things. We have omega to the omega plus 1, we have omega to the omega times 2, we have omega to the omega squared, we have omega to the omega to the omega. And those are already, if you try to picture those in some way, which is possible, but which I'm not doing here, those are already fairly complicated objects. And so we get to iterated powers of omega here. And all of these are still smaller than epsilon 0. Okay, let's do a little bit more about ordinal arithmetic. We recall the ordinal A, which we defined previously, and we define a new ordinal B, which is just omega plus 2. So what happens if we add the two? That's basically the same as omitting all the parentheses and then performing term-by-term addition. Now here the only thing that's interesting is we add the 4 from the left to omega, and as we've already seen in examples before, that just means the omega gets absorbed. The 4 gets absorbed. So what's left is the omega. So we have omega plus omega, that's just omega times 2. And then all the terms of smaller order on the right just get copied. That's just the 2 here. And all the terms of larger order on the left also get copied on the left here. If you would switch the order and add omega plus 2 on the left, then nothing interesting would happen, because all the terms of omega plus 2 are of lower order than the leading term of A. And so they would all be absorbed, and the result of the addition would just be A again. For multiplication, we've already mentioned that the distributive law holds. So we would first multiply omega by this ordinal a here on the left. And the result is that all that matters is the leading term here, not even the leading coefficient. So that gives us this term here, omega to the omega plus 1. And then we multiply this ordinal on the left here by 2. And that affects only the leading term. So the leading coefficient 3 here gets multiplied by 2, giving 6. And all the other terms just get copied over. Now let's do the multiplication the other way around. So in that case, again, we have distributivity. So each of these terms gets multiplied by omega plus 2 to the left. And except for the constant term, if we just consider the first 3 terms, if any of those gets multiplied by omega plus 2, only the leading term matters. In this case, that's omega. So that gives us these 3 terms here. And then the last 2 terms come from multiplying omega plus 2 by 4. And here the constant term is kept, but it's just copied, and the multiplication only affects the leading term. So we get the omega times 4 plus 2. Now let's look at exponentiation. So if we take a to the omega plus 2, again, distributivity holds. So we first take this thing on the left to the power omega. And for that, the only thing that matters, again, is only the leading term, not even the leading coefficient. So we have omega to the omega to the omega, and that gives omega to the omega squared. And that now gets multiplied on the left by the remaining power that we have to take here, taking this ordinal to the second power, and then multiply what we just had on the left. And you see that every term in here actually has omega to the omega squared. Even the last one has omega to the omega squared. That comes from the multiplication of this whole guy to the omega from the left. So what remains now is this guy squared. And that's just a multiplication that, like what we saw before, and that gives us all the other coefficients here. We can actually use parametric ordinals. So what we use here are parameters x0, x1, x2, x3, y0, y1, y2, and z to illustrate how the multiplication works. So the rules that I just showed you are not just special cases, but they hold in general. I've also written a little routine here called display, which will do automatically what I've done before. So it will display the inert, the not executed sum first, and then on the right hand side it will display the result of the execution, or actually sometimes even in a line below if things don't fit on the same line. So here we have an ordinal. Now all the exponents are actually integers to help illustrating things, and the coefficients, I've made sure that the leading coefficients x3 plus 1 here and y2 plus 1, and the constant coefficients x0 plus 1 and y0 plus 1 are actually non-zero, because the parameters can assume arbitrary non-negative integer values. So in particular, they could assume the value 0, but by adding 1, I've made sure that those are non-zero terms. So what happens if we add p and q? You see exactly what I said before. So the lower order terms in this case, x0 plus 1 and omega times x1, they get absorbed because they are lower order than omega squared, so they don't even show up in the result. And then I have the addition of omega squared times x2 with this, and that gives me the middle term here. And then all the lower order terms on the right are copied to the sum, and the higher order terms on the left are also copied. For comparison, if you do it the other way around, as I mentioned before, all the terms on the left are of lower order than the leading term on the right, so they get absorbed completely, and the result is just the ordinal on the right. Now, what happens if I do the same thing and just add a constant? So z is a parameter now. It's assumed to be a constant, so the constant will just be added to the constant term. So that's not surprising. For multiplication, what we see here is that if both ordinals have a non-zero constant coefficient, and that's the way I set up things, then if I do the product, then the order of the coefficients will be switched. So here I'm multiplying by an ordinal which has coefficients x index something on the left, and I have another ordinal which has coefficients y index something on the right, but in the product all the y's are on the left, except for here in the middle term, and all the x's are on the right. So basically by multiplication the order of the coefficient switches. And you can see the same thing if I do it the other way around. So now I have all the y's on the left in my product and all the x's, and in the result all of a sudden all the x's show up on the left and all the y's show up on the right. In particular, if I multiply by a non-zero constant, then if I multiply that from the right, it will only affect the leading term. I already mentioned that. And if I multiply by that non-zero constant from the left, then it will only affect the constant term. Here we can see that it is important for this last equation that z is actually non-zero, because if z was 0, then if that formula would hold, I would get this. But if I actually plug in 0, I get 0 as a result. So this here has a non-constant leading term. So this would be an example of the formula above, but the result is identically 0. So this formula really only holds whenever whenever the constant that I multiply by is non-zero. Couple more things which I also mentioned already. If the factor on the right does not have a constant term, then it completely absorbs everything from the factor on the left except for the leading term. And this is again what we see here. And for the constant, we've already seen what happens. Okay, let's look at some iterative products. So we define a simple ordinal with two terms here, omega times 2 plus 3. We can square it, we can cube it. And what you see is that the leading terms and the constant terms remain the same, and only the terms in the middle grow, but they don't grow as much as one would expect. So if you would multiply these as polynomials, then you would expect some binomial coefficients to creep in, but that's actually not the case. So the coefficients don't grow any further even we increase the powers. There is also a power command in the ordinals package. With it you can compute iterated powers. The normal power operator without using parentheses only allows you to compute powers with two arguments, so one base and one exponent, but here you can have multiple exponents. So let's see what happens if we iterate powers of 0. The result may be somewhat surprising, but that's already true for the integers. These are just integers powers, so the empty power is defined as 1. The power with no exponent is just the element itself. 0 to the 0 is defined as 1. If we take one more exponent, then we get 0 again, so this keeps alternating. Nothing interesting happens if we take powers of 1. They're just all 1. So what happens if we take powers of 2? So those look still fairly civilized, but if we take one more iterated power, we already get a fairly big integer. Now let's look at iterated powers of that ordinal b that we just had. So the first one is already fairly complicated ordinal with 6 terms. Now we take the third iterated power, and it doesn't seem to get any more complicated except that we get another base omega at the bottom, and that is confirmed by taking another power, so it doesn't get any more complicated than that even if we keep iterating. Okay, so we've talked about the principal arithmetic operations, addition, multiplication, and powering, exponentiation. There's also inverse operations, but they're not absolute, so they're only partial inverses. So let's look at these two ordinals. And for the inverses, we use function calls. So in this case, we take the subtraction, and this is a one-sided subtraction. So we're trying to subtract b from a on the left. And this is actually possible, and the result is this. And we do the test. So if we add the result, which is c, on the right to b, then we actually get a back. So what happens if we try to subtract them the other way around? That is not possible because I can only subtract from something that is bigger than what I want to subtract, and so I cannot subtract a from b because a is bigger than b, and so the result is null in this case. So that's the inverse to addition. There's also an inverse to multiplication, namely division, and that's actually a Euclidean division, meaning that there is a remainder, like for polynomials or for integers. So the diff operation has two results, a quotient q and a remainder r, and it has the expected Euclidean property that the remainder is actually smaller than what I'm dividing by. And if I multiply them, so if I take divisor g times quotient plus remainder, I get the original ordinal back. And there's also an inverse, a partial inverse operation for exponentiation. That's the logarithm. Now that has three results. The first result is the logarithm, so the exponent basically. The second one is a quotient, and the third one is a remainder. So here the logarithm is omega, the quotient is 2, and the remainder is omega cubed plus omega squared times 3 plus 5. And the properties are that the quotient is less than what I'm taking the logarithm, the g with respect to which I'm taking the logarithm. The remainder is less than g to the exponent. And if I take g to the l times q plus r, then I get my original polynomial back. If I iterate that, then I can represent ordinals in other bases than omega. So the Cantor normal form, which we've used here all the time and which you can see everywhere, is basically a base omega representation of an ordinal. But I can find a representation of ordinals with respect to any base, basically, as long as it's not 0 or 1. So for example, I can find a representation of the polynomial of the ordinal f with respect to the ordinal g. And that's what I see here. So it's basically g to the omega times 2 plus g to the 1 times omega plus 1 plus g to the 0 times omega squared plus 5. In particular, I can also find a base representation in base omega plus 1, for example. In that case, it's no longer true, and it wasn't true in the previous case either, that all the coefficients are integers. All the coefficients are, in general, just smaller than the base for my representation system. So in this case, all the coefficients are smaller than omega plus 1, and in particular, omega itself is allowed and appears as one of the coefficients here. I can also get a base 2 representation, and that may look a little bit funny. So obviously, all the coefficients are 1 here because the only coefficients allowed are strictly smaller than 2, so that's 0 or 1, and the 0 ones aren't even printed. And to convince ourselves, this is an inert representation using all the inert operators in order to convince ourselves that this representation is actually the same as my original ordinal f. I just apply the value command and I do get the ordinal f back. A couple of other things that can be done with ordinals which may not be all that well known out there. Since any two ordinals have, there's the Euclidean algorithm for ordinals, that means we have a GCD, but it's a one-sided GCD, it's a left GCD. So let's consider those two ordinals, u and v, and let's compute what their GCD is. And if you look at it, it happens to be that the GCD has almost exactly the same, basically consists of the common rightmost terms of the two input polynomials. But first of all, let's verify that it is actually a GCD. So it is divisible. Both input polynomials are left divisible by the greatest common divisor g. We can also compute the quotients. We can compute the GCD of the quotients, and that is actually 1, because, again, as you can see visually, there's no common terms on the right. So 1 is the only common term on the right that those two polynomials have. And we can verify that if we, well, that's by construction already. If we multiply g by its cofactor, we get input polynomial u back. If we multiply g by the other cofactor, we get the input polynomial v back. I already mentioned that the coefficients and exponents on the right agree of the GCD and of all of the input polynomials, and this is a general rule. And since we have GCDs, we can also factor. So here's a factorization of the two input ordinals u and v. And what happens when you factor is, we've already seen that before in an example. If you multiply two ordinals, then the coefficients basically get switched. And that's also the same that happens in factoring. So we start out here, for example, with an ordinal whose leading coefficient is x plus 1 and whose trailing coefficient is 5. And in the factorization, you can see that the leading coefficient on the very right and the previous constant coefficient on the very left. So basically, the coefficients in the factorization get switched. And since the GCD is a left GCD, that means in the factored form, we're taking off the leftmost factors, while in the expanded, in the Cantor normal form, we're taking the right common terms. Okay, so let's do the same thing to the GCD. So you can see that both polynomials have the same factors on the left, and that's exactly what the GCD returns. Let's also look at the cofactors, u1 and v1. And you can see they do not have a common factor on the left. So these factors, as is the nature in factoring, those are irreducible polynomials, and therefore there's no common factor. Okay, that concludes my presentation for today. If you'd like to know more about ordinals, you can go to the overview package of overview help page of the ordinals package. Which has a description of all the details of the data structure, of the operators that are available, of how parameters are allowed, and so on. And it also has links to all the commands of the package, so each package command has its own help page. And it also has some introductory examples similar to the ones that I've showed you today.